This is a great problem to demonstrate Bayes' theorem, so let's jump right into it. Let's suppose there's a box with 3 red and 3 blue balls in it, and we're going to take a ball out and not look at what color it is. And now the ball either has 3 red ones and 2 blue ones, or 2 red ones and 3 blue ones. We don't know because we took a ball out and we didn't look at it. So for part A here, it says we're going to remove a ball at random from the box, look at its color, and put it back. And we do the experiment 6 times, and every time the ball is blue. So what's the probability that it was a red ball that was initially removed from the box? And our hunch would tell us that it probably was if you pulled out blues every time, because there's one less red in that box. But we need to quantify this, and Bayes' theorem is a way to quantify that. So you have that big formula there, and we have probability of A and have probability of B given A, and all these scenarios. And so let's establish what probability of A is. So we're going to say the probability of A is, what is the probability that it was a red ball that was initially removed from the box? Okay, so we'll write that first as our first statement. And then our second statement, probability of B, is pulling out a blue ball. Okay, at the beginning, when there were 6 balls, 3 of each kind in there, what was the probability that I took a red out first? I had an equal probability of pulling out a red or a blue because they're even quantities. So the probability of A is 0.5. All right, now the other thing we need to look at, you'll see it down here in this part of the formula, what's the probability of A complement? So remember, A complement is basically what's the probability of not red, or really what's the probability that it was blue on the first try, and that's also 0.5. All right, so we're going to need both of those. Probability of A was 0.5, and probability of not A, or not red or blue, was 0.5. Now we have to get into this conditional probability. What is the probability of B given A? So what is the probability of getting a blue ball given that we did remove a red ball first? Okay, let's establish that. So let me write that down. Probability of B given A means the probability of a blue given that, and that's what that little vertical line means, is the words given that. Given that a red was pulled first. So if a red was pulled first, what that means is the probability of a blue at that point is 3 out of 5, right? Because one of these reds is gone from the box. It's the ball that we took out, and so the probability of a blue at that point is there's 3 blues and 5 total balls. So that's what that number, that first number in the numerator is 3 out of 5. And we have that number again down here, 3 out of 5, so that's the same probability of B given A. Then we have probability of A complements, part of our formula, and then probability of B given not A. So probability of B given not A is, what's the probability of pulling a blue if we had pulled a blue first? So if we had pulled a blue first, what's the chance that we pull a blue now? Now the chance of pulling a blue is there's 2 blues and there's 5 total balls. So this one is 2 out of 5. All right. So now we're going to put this whole formula together. Now also, they did say he performs that experiment a total of 6 times, and each time the ball is blue. So what happens here is every time we run the experiment, the PA and the P not A is always 0.5 because that was the first event, and now we have a second event, which is pulling a red ball or a blue ball after that. And so he's going to pull a blue ball 6 times. So what we have to do, and since he's putting it back and it's with replacement, we take 3/5 to the 6th power, and we take 2/5 to the 6th power, and that's what's going to go down here in the denominator. So let me write all of this out in a formula that we're going to type in the calculator. So I filled in that formula with all of its constituent pieces. The probability of A is 0.5 times the probability of B given A, which is 3 over 5 to the 6th power, because we're doing it 6 times, divided by 0.5 times 3/5 to the 6th power yet again. It's the same part, and then this different part in the denominator is probability of not red, which was blue, 0.5, times the probability of B given not A, which is 2/5 to the 6th power. So let me get the calculator out, and we're going to have to be careful here with our parentheses. So I'm going to take 0.5 times, and we're going to use parentheses here, parentheses 3 divided by 5, and we're going to raise that to the 6th power. All right, So we use the caret symbol to the 6th. Now we're going to divide that by, and I put parentheses here because I knew we were going to need them on the calculator. There's a lot of things in that denominator. So divided by parentheses 0.5 times 3/5 to the 6th again. And then we're going to add plus 0.5 times 2/5 to the 6th. So parentheses 2 divided by 5 and raise that to the 6th. And now we can close our last parentheses. And so we get 0.9192. So it wanted 4 decimal places here. All right, so we're going to put 0.9192 is this first answer. And excuse me, when we round that, we look at the 5th decimal place as a 9, so it becomes 0.9193. So this first answer up here is 0.9193. All right, let's go see what part B says. So part B gets a little bit more complex. Ray removes the ball at random from the box, observes its color, and puts it back. He does it 75 times. So out of those, the ball was blue 47 times and red 28 times. What's the probability that a red ball was initially removed from the box? We're going to answer the same question again, but now this probability of B given A is a little bit trickier. Let's scroll back up. Our probability of B given A was the probability that a blue was pulled 6 times given that a red was pulled first, and that was 3/5 to the 6th. Our probability of B given A now is what's the probability that I get a blue 47 times and a red 28 times. So let me write out the formula for what I just said. So in that formula we have to work out these two things, the probability of B given A. So what's the probability of getting 47 blues and 28 reds given that a red was pulled first? And then the other one that we need in the denominator was what's the probability of 47 blues and 28 reds, but given that a blue was pulled first. All right, so what the probability of 47 blues is the same as the probability of blue before. If a red was pulled first, there were 3 blues left out of 5 balls left, and that happens 47 times. And then there were 28 reds, so the probability of a red, if a red was taken out first, is 2/5, and that happened 28 times. Now the probability of B given a blue, or A, or not A, or whatever you want to say here, that one is what's the probability of pulling a blue given that a blue was pulled first? Well, the probability of pulling 47 blues, if a blue was pulled first, there's only 2 blues left out of 5 balls, and it happened 47 times. And the probability of a red at that point now, that's 3 out of 5, and that's going to be to the 28. So all of that goes where right here we had 3/5 to the 6th. We're going to put all of this stuff right here. So our probability of B given A is now all of this stuff. All right, and our probability of B given not A was just 2/5 to the 6th before, and now that's going to be all of this stuff. So we've got to be very, very careful now putting this into the calculator. So let me pull the calculator up, and I'll show you what that should look like. So I've written out the formula here as we're going to type it in the calculator, and you can see here these two things. If you didn't notice it the first time, if we go back up to Bayes' theorem, let's go back up and look. Again, I pointed it out earlier, but PA times P of B given A, PA times P of B given A, the numerator is the exact same as the first half of the bottom. So I've kind of intentionally written it that way. The fraction bar should, of course, come on over here. It's over all of this. But I did want to emphasize here that these two things are identical. All right, we typed this in the exact same. And the thing that's going to be different is the end of the second half is where we basically flip-flop the fractions and put 2/5 to the 47 instead of 3/5 to the 47. Now, since you don't want to sit here and watch a YouTube video of me typing in the calculator for a minute, I have already typed it in. And so there it is, all typed in. If you want to pause the screen and make sure yours looks just like that as you type it in, that's fine. So I'm going to go ahead and press enter here, and we get 0.9995, and that is the correct answer. So now we got to go look at part C, which is just an understanding question to make sure we understand what just happened here. So I brought over part C there and just laid it on top of the rest of the problem. It says many people intuitively think that the first experiment, Nate's experiment, gives more convincing evidence than Ray's experiment, the one we just did. Explain why this is wrong and choose the correct answer. This is wrong because Ray chose the red ball more times than Nate. No, that's actually not what happened. He chose the red ball less times. This is wrong because Ray performed the experiment more times, or this is wrong because Ray chose the blue ball more times than Nate. As a percentage, he did not choose it more times. He chose it 47 out of 75, whereas Nate chose it 6 times in a row. But it's wrong because of part B is the correct answer. This is wrong because Ray performed the experiment more times. We got more and more confident the more times Ray did this experiment and poured the blue ball 47 times and the red 28 times. The number of times that we do the experiment, it makes us more and more certain that it was probably a red ball that was taken out first. And it's possible that Nate got lucky, if you want to call it luck, that he had pulled the blue ball out 6 times, but you could possibly pull the blue ball out 6 times even if you didn't take any balls out. And so this is kind of a good explanation of Bayes' theorem. There is a very excellent Khan Academy video that's a little bit more interactive than this and shows a great example using coin flips. And it shows how Bayes' theorem is derived, and it's a pretty cool video. So I'm going to put a link here up in the corner so you can go look at that. And if you have any questions, let me know.